Aloha and welcome to Business 621 Lecture 1 screencast on the basics of statistical inference. What we're going to do today is we're going to build on our uh, knowledge of descriptive statistics and apply it to making inferences or estimates about population characteristics from samples. So a little bit more on that later. But you can look through here and see the basic topics we're going to talk about. Now there are much more uh, extensive kinds of things in inferential statistics than this. This is just the basics, but this should give you enough foundation to actually move forward with other kinds of techniques and methods. Most of the other things are just variations on these basic things. One thing I want to point out, though, is you'll notice that we talk about things like inference for a single numerical variable, inference for a single categorical variable, inference for two categorical variables. You'll see kind of a running theme that just like in descriptive statistics, that after we understand what variables we want to look at what kind of data we're working with, and that will determine what kind of statistics we do. So more so than the questions that we want, they tend to be the same depending on what the kind of data is, but how we work with it will be determined by what kind of data it is. So we always want to keep in mind that we should know what is the data that we're working with it. What are the variables? Is it numerical? Is it categorical? Is it numerical and categorical? Blah, blah, blah. So keep that in mind as we move forward. The statistical methods that we're going to look at are estimation and hypothesis testing. And they're called inferential statistics because they differentiate from descriptive statistics in that in inferential statistics we're going to use descriptive statistics to see what we can infer or what we can sort of guess or say about something. And this something, the way that the general theme is that we have a population of things that we're interested in, and then from a sample of that population, we will look at the descriptive statistics of that and use that to say what we can infer from those descriptive statistics about the population. And the two main methods of things that we're going to look at are estimation and hypothesis testing. They're both related. So let's start with estimation. Now, to understand what estimation is, we start by understanding once again what's the difference between a population and a sample. So a population is any group of things that we're interested in. Now the interesting thing about a population is that it's not just data. It's actually a group of things that we're interested in that may or may not be observable, so or even accessible. Some examples of that might be that, let's just say we want to look at the average, the income of the American, the average American citizen or something like that. And now if we're talking about the population of current American citizens, that in one sense, if we freeze it in time, then that is a population that we can observe. But if we don't freeze it in time, we see that the population of the United States, in terms of citizenship, changes. It's constantly increasing and decreasing, or perhaps increasing, but it's changing. New people are added all the time, new people are born, etc., etc. People immigrate. So if we don't fix it at a particular point in time, that population actually is not observable. Because we can only observe part of it at any given time. We cannot look at it. But nonetheless, it does actually make sense to talk about a characteristic of that population. And one characteristic we might be interested in is, say, the mean. And the mean of that population, let's say we're looking at the mean income of U.S. citizens, even though it's changing over time. Interestingly enough, we can even talk about a population of all U.S. citizens, past, present, and even future. So if we add future ones, that's kind of an interesting one, and it shows how the power of statistics, that we actually can do statistics about a population that has data that hasn't even occurred yet. So not only is it not something we can get our hands hold on because it's changing, but it may not even exist yet, and yet we can still talk about it. And that's one of the power the powers of statistics. Now, when we talk about a characteristic of a population, we usually mean some characteristic of some either a numerical characteristic of that population. Usually we talk about the distribution or a characteristic of that distribution for that population. So when we talk about a characteristic of a population, we will use a Greek letter, say mu. By convention, mu would be the population mean, and and we only look at the population mean for data that would be numerical. And we assume that when we have a population that that characteristic is not known. If the population turns out to be something that is very easily accessed and observed, let's just say the income of Dilemma students in our class, then all we have to do to get that population characteristic is ask every student in the class, the 30 or so odd people, what's your income? Sum up those incomes, divide by the number of people, and we have it. So that would not be an unknown parameter. It would be easily gotten. But if we look at the income, the average or mean income for the U.S. citizens, that is not easily gotten. Not only is it not practical for us to ask hundreds of millions of people what their income is, it's changing all the time, and so is the population, so we can't even get it. So in that case, it's actually unknown. Now the interesting thing is that even though it's unknown, that doesn't mean we can't say things about it. And what we want to do is say, take a sample of that population that we can access, that we can observe. And from that sample, we will calculate a statistic. In this case, the sample mean. And when we talk about a sample statistic, we will use the not Greek letters. In this case, for the mean, the convention is to use something like x bar. So x bar is just a notation to refer to the sample mean, whereas mu is the population mean. So we can distinguish one from the other by whether we use Greek characters or not Greek characters. And say we calculate that sample mean. Now it's a statistic because it's something that we can actually compute, meaning we take the values from the sample, sum them up, and divide by the total number of them. And let's say it was 50. Now the question we're going to know is how good is this as an estimate for the unknown parameter mu? In other words, this is a sample mean. Presumably it has some relationship to the unknown one. Why do I say that? Well, imagine that if this sample gets larger and larger and larger. As this sample gets larger and larger, say it tends towards the entire population, then the computation of the sample mean will converge towards the actual mean. In other words, once I get the entire population, that sample, if it is the entire population, is no longer an estimate. It is the actual population characteristic mean. So in other words, that there is a relationship between the sample mean and the unknown population mean. How good it is really what we care about. In other words, how accurate it is. And it obviously has something to do with how big the sample is, but it also has to do with a number of other characteristics and issues that we'll talk about. So a couple of important points to point out here. So one, the sample is a subset of the population that we can observe. From that sample, we do a computation or a statistic that is somehow related to the thing that we're interested in. And the question about estimation is how good of an estimate or an approximation is that sample to the thing that's unknown. So we call that the estimation problem. Something to point out here is it says that it's a random sample. So the issue here is that when we're doing estimation, we pretty much always assume that the sample we take is random. Random meaning that we did not select any of these points for any particular reason. Let's take, for example, the income of U.S. citizens again. Well, let's just say that our sample happened to be something convenient. Let's just say we went over to Kahala and we said, well, let's ask everybody who lives in Kahala what their income is. And then we sum that up and divide by that number of people that we asked, and we let that be the sample estimate for the unknown mean. Well, that's not going to be terribly representative of the population of the United States. Why not? Well, people in Kahala tend to be rather wealthy, and so the values that we're likely to get from them are going to be biased upwards or skewed on the higher income stream. That would be very different if, say, we went to Detroit and asked people in Detroit what their income is. Maybe their income tends to be a little lower. So in other words, if we are not random about this, if we are selective, then we will end up biasing our results, and that this approximation will not be representative of what the actual mean is. It will be biased or skewed one way or the other. And that means it's not terribly helpful. So we assume that the sample we have is random. Now, exactly what it means to take a random sample is a rather painful subject, so we're not going to talk too much about that. We're just going to go with our intuition here, which means close your eyes and just grab stuff from here. Okay, we'll just assume that that's our definition of random. Now, once we have an estimate, this is a point estimate, we make a statement about how good that estimate is. And when we make an estimate of how good it is, we can't just give a simple value. Usually we can express how good it is by giving it a range. So the value that we're looking for is between 40 and 60. Well, that's one way of looking at it, but then of course we need to know sort of, well, okay, maybe it's between 40 and 60. That kind of pins it down a bit, but we want to know, well, how sure are we that it's between 40 and 60? So we might say something like it's 95% confident. And we have to talk about precisely what this means. In statistics, all of these things have very careful, precise definitions so that we're not ambiguous and that we're also reliable. Okay, so estimating unknown population parameters. In our class, we're only going to look at a few population parameters of interest. In practice, of course, you can look at anything about a population that you might be interested in, and there's usually a sample statistic that will do that. But we're going to look at things like the mean. And when we talk about the population mean, we'll use the Greek letter mu, and then we'll talk about the sample statistic, or the estimator for it, being x bar. Similarly, now that would be for numerical data. For categorical data, we might be interested in the population proportion, and then we would estimate that with the sample proportion, which we'll denote by p. We might also be interested in the standard deviation. The standard deviation of the population we'll say is sigma, and for the sample, little s. We also might be looking at differences of means, and we might look at the differences of the sample means. We also, in our class, are going to be interested in things like the median, and but typically in other practices, especially if you're doing research, you might be interested in other parameters like correlation coefficients, covariances, and other various things. You can look at estimates for anything, but these are very common. So in terms of estimation, we have point estimates and interval estimates, and let's look at what those are. A point estimate is a single value, and we take a bunch of observations or random samples, and we take that random sample and we compute our estimate from a statistic, and that is indeed an approximation for our population parameter of interest. The problem with that is that we don't know how close it is, what error there might be, or how confident we are that that is a good approximation for it, or a representative approximation for it. So say we say our sample mean is 3, we call it a point estimate because it's just a single value, it's just a single point. And while it certainly says that our population mean might be about 3, we don't know how close it is to really 3. How sure are we that it is near 3 or actually is 3? An interval estimate is one step towards dealing with that question by providing a range of values. Now, the range of values will be based on, again, a sample, presumably a random sample, And what that does is it tells us how close we are to the unknown parameter, or how accurate it is. So when that interval says it's between this value and this value, on a low end and a high end. And the idea is that the smaller that interval is, the more accurate our estimate is, because the smaller the range is, means we pin that value down between a high and a low. So we sort of capture it, right? So we might say our unknown population mean lies between 50 and 70. So even though we don't know what value it is between 50 and 70, we know that it's somewhere in that range. And the smaller that range is, the more accurate it is. Obviously, if I said the population mean lies between 60 and 61, that leaves far fewer choices than between 50 and 70. So the length or the size of the range of the interval determines how accurate we are. Now, what's this business about 95% confidence? The 95% confidence comes in to say that we need to know kind of, well, even though that's an estimate, and we know it's between 50 and 70, or we think it's between 50 and 70, we could be wrong. And so when we say 95% confidence, we mean that 5% of the time it's actually not going to be between 50 and 70%. So 95% confidence means that 5% of the time I'm actually not going to capture it in there. And it's very important that you understand what I mean by capture. So let's talk a little bit more about that and what confidence are. So confidence level, you're going to hear this term quite a bit. Confidence level is the probability that the unknown parameter falls within the interval. So again, we want to know if we give a range, say, oh, it's somewhere between 50 and 70. We think it's somewhere between 50 and 70. We want to know, well, how sure are we that it's between 50 and 70? And one way that we can express that is with a confidence level. So the confidence level we denote by 1 minus alpha percent. And it's kind of curious that we say 1 minus alpha percent, because alpha is what we call the level of significance. And so alpha is the probability that the parameter is not within the interval. So in the case that we were talking about before, we said with 95% confidence, the mean population parameter lies between 50 and 70. So what alpha is 5%. Means that 5% of the time, it's not going to be between 50 and 70. 95% of the time, it is. So that's 1 minus alpha, 1 minus 5%, 95, right? If I take 1 minus 95%, I get alpha, which is 5%. So they're kind of opposites of each other. Now, typically for confidence levels, we choose confidence levels 90, 95, and 99, or anything between 90 and 99%. The reason for that is that, well, there's a relationship between how confident we want to be and the size of the interval. So the size of the interval tells how accurate it is and how useful it would be. So let's just imagine for a moment that we want to be 100% confident. Why is that a bad idea? Well, to be 100% confident, let's think about what we'd need to do, what interval size we'd have to have. Let's just say that we're estimating, once again, the mean population income for U.S. citizens. Well, we know it's going to be at least no less than $0. I guess you're not going to have negative income, but we don't really know how big it can be. In principle, it could be arbitrarily large. Now, I know that Bill Gates certainly has a lot of money and has a huge income. It's not infinite, but we don't really know how large it can go, and somebody could just make even more than that. So in a practical level, it can't be infinite, but we can't really be sure how big it can be. And even though there's only a few people that might have that, we still have to take them into account. So what we'd have to do to be 100% confident, we'd have to choose an interval between 0 and infinity. So to be absolutely sure, 100% sure that we always know what the mean population income for U.S. citizens would be, we'd have to have an arbitrarily large interval. anywhere between 0 and 100, no, 0 and infinity. Well, that is not terribly useful as an estimate, right? I mean, it doesn't really give us any information. It's terribly inaccurate. It just says, yeah, incomes are some value, right? Greater than 0. So that's not very useful. So what we do is we allow ourselves to be wrong. So we allow ourselves to be wrong, say 1% of the time, 5% of the time, or 10% of the time. Being wrong more than 10% of the time is usually not considered high confidence, so we don't usually accept it. Now, you could use lower confidence levels, but they're usually by convention not acceptable, because you'd be wrong too often. So let's just say we allow ourselves to be wrong 1% of the time. Well, if we allow ourselves to be wrong 1% of the time, let's imagine U.S. Citizens' income again. Well, look, let's say for most purposes, I'm really pretty sure that nobody in the United States has an income of more than, say, $10 trillion. I mean, that's a ridiculous amount, right? I mean, I could almost be 100% sure nobody has $10 trillion, but I'm not absolutely sure. But maybe I'm certainly 99% sure that nobody has an income of more than $10 trillion. So instead of giving an interval between 0 and infinity with 100% confidence, maybe I can say with 99% confidence the mean income of U.S. citizens is between 0 and $10 trillion. Great. Okay, and I would only be wrong maybe 1% of the time. Well, maybe I'm willing to be wrong a little bit more. So say I'm willing to be wrong 5% of the time. In that case, I can narrow my interval even more. So I said, well, I'm pretty sure that not many people, not maybe more than 5% of the people, have an income more than, say, $1 billion, right? $1 billion. So maybe with 95% confidence, I would say that the mean income of U.S. citizens is between 0 and $1 billion. Now, I could be wrong, maybe, but I'm not going to be wrong more than 5% of the time. And then you can see that the lower the confidence, the smaller the confidence interval can be. So, but the problem is it increases my chance of being wrong or not capturing it. So I can be more accurate or I can be more confident, but I can't be both. So let's talk a little bit more about what intervals and confidence levels are. The way that we're going to make our estimates, let's just say that we're making an estimate of the population mean. We're going to make an estimate by looking at the sample mean. Now the sample mean, we can consider the distribution of all sample means. The distribution means that if we take a random sample and we calculate the sample mean x bar, right? And then we throw that sample back into the population and we take another random sample and calculate x bar, you notice that those values, because it was a random sample, those sample means will be different, or it's very, very likely they'll be different. If we look at the distribution of all the values of the sample mean, let's assume that it's going to be bell-shaped or normal. It turns out that in most cases it will be bell-shaped or normal, and that's another amazing thing about statistics. But let's just take it on faith for now that the sampling distribution of the sample mean is bell-shaped, meaning that if we take a random sample and calculate the sample mean, and then we look at the histogram of all those sample means, it will look bell-shaped like this. Well, what can we say about making an estimate for it? So in other words, if we have a sample estimate x bar, right, how can we generate a confidence interval or confidence interval using that? Well, we know that the sample means will be spread out between negative infinity, infinity over here, or whatever it is, according to this bell shape. Now, right in the middle, we're assuming that if we take an infinite number of these samples, right, that the average of all those will be the actual population mean. So if we could take an infinite number of random samples, right, and look at the average of all those, it would be the population characteristic that we're interested in, which is the population mean. And that's going to be right here in the middle. So the question we have is like, okay, how close, given an x bar, what size interval could we get so that we know that we capture this mu 1 minus alpha percent of the time, or equivalently, we don't capture it alpha percent of the time. So let's say that we want to figure that out. So the way we can figure that out is if it's bell-shaped like this, right, then we know that we want to capture this center point here. Yes? So if we choose a value between here and here, right, then the probability that I'm outside of it on the high side is alpha divided by 2, and on the low side alpha divided by 2, because it's symmetric. So the probability that a value, that a sample, a random x bar is in this interval, right, is going to be 1 minus alpha. Let's make this more concrete. Let's say alpha is 90%. I'm sorry, alpha is 10%. So 5% of the time I'm going to be higher than this value. 5% of the time I'm going to be lower than the low value. And 90% of the time I'm going to be between here and here. Why is it 90% of the time? Because the area under this curve, okay, is 90% of the area under the curve. This would be 5%, that would be 5%. So this puts a precise definition to what we mean by 90% confidence. So let's say 90% confidence. Alpha would be 10. 1 minus alpha would be 90. What that means is that if I take a random sample and I calculate its sample mean, x bar, then this interval here will capture the mean, the population characteristic, 90% of the time. It will fail to capture it 10% of the time. Okay, so you'll see that I calculate a mean, a sample mean, and I look at a distance away from it on the low side and distance away from it on the high side, and I see, does that interval capture the middle? In this case, it does. In this one, it does. Notice it's shifted over. It's shifted over because the sample mean now is here. Oops, is here instead of over here. Okay, the size of the interval stays the same because we wanted to capture it 90% of the time. Now let's say I capture another random sample, and its sample mean is over here, going above and going below, so that I capture still 90%. Does no longer captures the population mean. So in this case, it's not capturing it, so it escaped. And then this one, it did. So if I did this, let's say I'm looking at 90% confidence. If I did this 100 times, if I have 100 of these confidence intervals, then 10 of them will be red and not capture them, and 90 of them will capture it. So that is a precise meaning of what we mean by 90% confidence that the value is between here and here. Okay, it means that when we generate these confidence intervals, that 90 out of 100 times we're going to capture this. Okay, if that's a little confusing, don't worry about it. In practice, it's a lot easier to deal with. So the question is, what affects the size of this estimate interval? Okay, well, one of them, of course, we already talked about, is the sample size. That the more samples we have, the smaller the size of the interval, the more accurate the estimate is going to be. And again, the reason for that is that the larger the sample, the closer it gets to being the population itself. And so once we become the population, it's no longer an estimate. So that interval better be, very, very, very small. The other thing that affects the size of the interval is how variable the data is, or the dispersion of it. So in other words, the more the data varies, like in terms of standard deviation, for example, then the larger the interval is going to be, because the values are bouncing around a lot. If I take a random sample of it, then what's going to happen is that it's going to be spread out, more likely to be spread out. So the values are going to be spread out over a larger range, which means I'm going to have to use a larger interval to try to capture the value that I'm interested in. And of course, the level of confidence. Again, the higher confidence I want, the larger the width, but the higher, but the lower the accuracy. So if I want uh, higher confidence, I get a larger width to capture, because I want to capture more of the things, be sure I capture it. If I'm willing to reduce that confidence, then I can be more accurate, but I have lower confidence. So there's always a trade-off between sort of confidence and accuracy. Let's talk about our first method. Now, our first method is, let's assume that our data is numerical, and that from that data for that population, we're going to be interested in making an estimate of the population mean, mu. We're also going to assume that for not only is the population mean unknown, we're also going to assume that the standard deviation of that population is unknown. If it's the reason why we assume that is that if we knew what the population standard deviation is, we probably would know what the mean is, because there's a relationship between the population standard deviation and the population mean. So if we don't know one, we probably don't know the other. So that for practical reasons, we don't look. But it is possible that if we do know what the standard deviation is, we still can make an estimate, and we'd use a different technique for that. Those arise in the case where you want to set what the standard deviation is. So say that you want to assume in theory that it is this, or you want to force it to be a certain thing. Then you can say what is the estimate. But that's pretty uncommon. So usually this is unknown and that's unknown. Now for the data estimate that we're going to, for the numerical data that we're going to make the population estimate for, we're going to assume that it is normally distributed. It turns out that if we have enough sample points, that this is not an issue. But if you only have a small number of sample points, this is. And the reason why I want to assume it's normally distributed is for this, because we want to be able to precisely calculate the probability that I'm in an interval or I'm not in an interval. So to calculate that probability, I have to know the distribution. So if I know the distribution is normal, then I can calculate what's the probability that I'm this or greater. What's the probability that I'm that or smaller. And because of that, I can calculate what's the probability that I'm in or not in this confidence interval. So to calculate those confidence intervals, to put precise meaning to 95% or 90% confidence, I have to assume that the population is normally distributed. So let's just take an example here. Let's just say that I'm analyzing the time it takes to do a particular task, and I observe a sample of times to complete a task of being 3.6 minutes, 4.2 minutes, 4.0 minutes, 3.5 minutes, 3.8 minutes, and 3.1 minutes. So this would be our sample. We would like to know what is an estimate for the mean task time in general for the population based on this sample of observed task times. And let's just say we want to be 90% confident. So we'll allow ourselves to be off or wrong 10% of the time. How accurate of an estimate can we make? Well, what we can do is we can use Megastat to do the calculations for us. Now, we could go through all the technicalities of how to do this, but I don't think it's particularly illuminating. I think you know enough of the theory behind this already without having to know how to do the calculations. Let's just let Megastat do the work. So what we would do is we'd open up Megastat and calculate a confidence interval under the confidence tab. And we would calculate, let's take a look at what that is. Let's see if I can get that up. Okay, so let's say I have this data. let's say I have this data, and so what I want to do is go to add-ins, Megastat, and I'm looking for confidence intervals and sample size like this, and see it brings up this window similar to this. Notice that it asks for the confidence interval mean, confidence interval p if it's a if depending on what I'm estimating here. It's asking for the confidence interval for the mean, confidence interval for the population proportion, sample mean, sample size, and that kind of stuff here. Okay, so if I compute, let's see, the sample mean here, so I just say average here and calculate that like that, I get 3.7. Okay, and I calculate the sample standard deviation. And now let's go to Megastat, confidence intervals, 3.7, standard deviation of 0.389872. Sample size is 1, 2, 3, 4, 5, 6. And I want my confidence level to be 95%. Now what I want to do is, you see it says Z or T. And the reason why what I would choose between the z-test or the t-test depends on the distribution I'm willing to assume. The z-test is if I know the standard deviation and I want to estimate the unknown mean. The t-test is if I have an unknown standard deviation and an unknown mean, which is our case too. So in that case I'll do a preview and you'll see I get an estimate of 3.291 and 4109. Okay, so let's hide that. And what that says, I say again, t-test, that was 95% confidence. I guess 90% confidence, you get the idea. Is that with 90% confidence, the population mean times will fall between 3.379 and 4.021. Okay, so that's all we're going to talk about with confidence intervals. To calculate confidence intervals of proportion, it's the same thing. You just choose the sample proportion instead of the sample mean. And for any other estimate for other parameters, as long as you have something calculated, that's how you do it. Now we'll talk about hypothesis testing. Hypothesis testing is where we're going to take this idea of confidence interval and apply it to answering questions. So rather than estimating from a sample, estimating a characteristic of a population from a sample, what we want to do is ask questions about a population parameter and answer it based on the population, the sample. Okay, so the idea is, do we have evidence from the data to support or refute what we call a hypothesis? Now, a hypothesis in statistics is something very specific. A hypothesis will be specifically a question about a population parameter. Okay, and we say like a belief about a population or a speculation about it. So again, in statistics, a hypothesis is always a question about a population parameter. We don't just talk about, do people prefer, Ritz crackers over Triscuits? That's not a, well, I guess that could be formulated as a statistical hypothesis, but that's not in particular a statistical hypothesis. Or what we want to talk about specifically is a parameter of interest, like the mean or a proportion or say a slope of something, some value that we're interested in. We have to state what the hypothesis is, and we have to actually write it out precisely in a particular way if we're going to test the hypothesis. So let's just say I believe the mean GPA of this class to be 3.5. Okay, well, what we want to know is there evidence based on a random sample to support or not support this statement that the mean GPA of this class is 3.5. So here's another question. Let's take a hypothesis test. Say we might want to look at the population of people in the, let's say the world population. Let's say of all the people on the planet, the population mean is 50. Now that might be a speculation that the average or population mean age is 50 years old. Well, we can't really look at it's not practical for us to get the age of all the people in the planet, and of course it's changing all the time. We can get a small sample, a random sample of it. And let's just say we take a random sample and we find that the random sample gives a sample mean of 20 years. Well, 20 is pretty far away from 50, right? So the question would be, well, if this is an estimate for the population mean, is it close enough for us to believe that the population mean is in fact 50, or is it far away, so far away that we don't believe it's actually 50? So the closer this is to that value, the closer the estimate is to the hypothesized value, then the more likely it is that this statement is actually true. If it's not close, we would reject it and say, I don't think that the sample, which is the evidence, supports that this is true or not. So the question is, based on the sample, is that sample provide evidence that this is either true or not true? And if it's true, we accept it. If it's false, we say we reject it. So the problem is how do we know how close is close? Well, we can use our idea of confidence intervals to do that. So the way we do that is if we hypothesize that the true value, or the value of the population mean mu, there should be, if it really was what we think it is, then if we take a random sample and calculate its sample mean, say x bar, then it should be, if by definition, it should be pretty close to it. In other words, the probability that I get that by random chance, right? The probability that I'm off by random chance is how, like maybe I just chose a bad random sample. Like maybe I just happened to be taking a sample of people at a college for which maybe the population sample, the sample for that would be smaller. Maybe it was biased without realizing it. So we call the p-value as the probability of getting a certain value by random chance. And what we want to know is that p-value is small. If the p-value is small, meaning that the probability of getting a random sample value by chance is really high, then that actually means that the hypothesized value that we're looking for is probably not true, and as we're far away from it. If the p-value is very small, or actually I should say that again, if the p-value is very high, then we don't really know if the hypothesized value is correct or not. Because we don't know if we got that by random chance. It's in other words, we could have just gotten it by random chance. There's a high probability. If the p-value is small, then the likelihood that we got that value by random chance is very unlikely. And so we would say that that must mean that our hypothesis value is wrong, and so we would reject it. Okay, so that's confusing. Let's take a little more close look at that. So let's take our sampling distribution of sample means again, and instead of calculating a confidence interval, we are going to calculate a confidence interval. What we want to do is say, well, let's say a hypothesized mean is 50, and then we get a sample of 20. Now, if this is the sampling distribution, the actual mean is right in the middle here. What is the probability of getting a value of 20 given that this were true. If this were really true, how likely is it that we'd get a random sample mean from a random sample of 20? Well, you can see that it's pretty far off on the bell curve. In other words, it's the probability of getting this or lower, right, is pretty small. In other words, the probability of getting this value or higher is quite large, because you see the area between here and here is really large. Okay, so what does this mean in terms of p-values? So let's imagine that if this were the actual mean, then a 90% confidence interval might be, say, between here and here. So in other words, we want to look at what's 90% of the curve centered here at the true population would be, say, from here to here. So if we look at the area from here to here, maybe that's 90% of it. So that means that 5% of the time I would be outside the interval, this side, and 5% I would be that side. So in other words, if I had a 90% confidence interval from here to here, right, then 10% of the time I'd be either outside of it this way or outside of it that way. In other words, if I got a value 20, the probability that I'm not in that confidence interval is very small. In other words, the probability that I'm not in there is very small. It's like this plus that. So say less than 10%. So if it's less than 10%, which would be our p-value, then we'd say, well, wait a second, that's really small. So it's unlikely that I would get a value like this of a random sample if this were the actual population mean. So in this case, I would reject the hypothesis that the population mean is 50, because getting a random sample value of 20 is very unlikely if that were true. Now that may be a little confusing, but in practice all you have to do is remember the simple rule of thumb. If the p is low, the null's got to go. The p is low, the null's got to go. In other words, if the p value, meaning the probability of being outside the confidence interval, is too small, then you reject the hypothesis that you're making. Let's take a look at that in more detail. The first thing we need to do is set up a hypothesis that we can actually test. The way we do that is we set up two alternatives. One we call HO, or H naught, or H null. This is called the null hypothesis, meaning the nothing. It's the one that we sort of say we take for granted to be true if we don't have evidence to say otherwise. We call it the straw man because we sort of set it up because we don't actually believe it's true, but we want to find evidence to reject it, to say that it's not true. Now, when we set up the null hypothesis, it always has to be the thing that's stated with the equality or equal sign. So in our case, if we're looking at the population mean, we'd have to say the population mean is equal, less than or equal to, or greater than equal to some value. And that will always be what's in the null hypothesis. The alternative is going to be the exact opposite of the null. So if I say that the population mean equals something, then the alternative would be that it's not equal to that something. So if I say the population mean equals 50, then the alternative would be the population mean is not equal to 50. If it's less than or equal to, then the opposite is greater than. If it's greater than or equal to, then it's less than. So it always has to be the exact opposite, so that only one can be true. It's not, you can't have both H naught and HA be true. So the alternative always has the inequality, the null has the equality, and you always write that out by convention, and the tests that we compute will always assume that that's the way things are written. So, for example, we might say the alternative hypothesis is mu is less than 3. That means that H naught would be mu is greater than or equal to 3. And we would just write those both down. Let's take an example. Let's say that we're trying to test that the population mean is not 3. Well, first thing is we state that statistically. Population mean, we'll use the Greek letter mu, by convention means population mean. The English not 3 means not equal to the value 3. The opposite of this would be, exact opposite is mu equals 3. We say that's mutually exclusive and exhaustive, meaning that mu has to be at least one of these things and can't be both of these things. So exhaustive means that it has to be one or the other. Exclusive means it can only be one. Now, because this has the not equal, this is going to have to be the alternative hypothesis, or H sub A. This one has the equality, so this is going to be the null hypothesis, or HO, or H naught. We call this a two-tailed hypothesis because not equal means that I can be not equal to mu by being either less than 3 or greater than 3. So in other words, I can be not equal by being greater than or less than. In other words, I can be at in terms of the confidence interval, looking over here, I can be outside, say, my 90% confidence interval like this. I can be outside of it by being less than it, that's one tail, or greater than it, that's the other tail over here. There are possibilities of one-tailed hypotheses, meaning that I don't care if I'm less than, I'm only greater than. But when I have a not equals, it's a two-tailed. If I was using a greater than or less than, it would be a one-tailed. Let's try another one. What if the question was, is the population average, or the amount of TV viewing, equal to 12 hours? So the first step is to decide, well, what do we mean by population average? Well, if we're going to assume that the viewing time is normally distributed, then we might look at the population mean to represent the average. So that characteristic is what we'd be interested in. And so we state the question statistically. Mu, meaning the population mean average, is equal to 12, right? And the opposite is not equal to 12. Since this is the not equal, that's going to be the alternative, and that has the equality, so that's going to be H naught. Again, it's a two-tailed test. What if we wanted to say, is the population average amount of TV different from 12 hours? Well, that's basically the same thing. Once again, different than 12 hours, mu, population average, different, not equal to 12. Again, the opposite's that, and then same hypothesis holds. How about this? What about the average amount of spent in a bookstore is greater than 25? Again, we'll assume that average amount of spending, let's say that spending is normally distributed. And so what we mean by the average would be the population mean. So we say the population mean average is greater than 25. So mu greater than 25. The opposite would be greater than equal to. This doesn't have the equal sign in it, so it's going to be the alternative. And this has the equality, so it's going to be the H naught. This is a one-tailed or a right-tailed test. So let's see why it's a right-tailed test. Or one-tailed is easy because I'm looking at it's greater than. But why is it to the right? Well, right, or sometimes they say positive also. Let's take a look at the alternative hypothesis. Mu is greater than 25. I'm going back to our bell curve here. How can I be, the alternative is greater than 25 or less than 25. Now, I would say that it's greater than 25 if the actual population mean, if I get the sample, right? If the sample is greater, let's say that's 25 here, if the sample is that or more, right? If it's, in other words, if I have a confidence interval here and I'm outside the confidence interval on the high end or to the right, right, then that would make it greater than. If I'm down here on the left side, if I'm outside the confidence interval on the left side, it doesn't matter because it's not greater than the hypothesized one. So the easiest way to remember which is right, left, whatever, is to look at the alternative. And the way I remember it is that if the alternative is less than, has the less than sign, that begins with the letter L, right? Less means lower or a lower-tailed test. Less also means left or a left-tailed test. So left, if it's less, means less. Less means left or lower tail test. Otherwise, it's right or upper tail test. How about another one? Is the average cost per hat less than $20? Once again, we'll say average meaning the population mean. Less than 20, that's less than 20. The opposite's greater than or equal to. This is the one with the not equal or the inequality in it, so it's the alternative. This is the equality, so that. And it's a left or lower tailed test or one tailed test because it's the less than sign, right? So less, left, less, lower, or one lower tailed test. What about the level of significance? The level of significance represents the tail probability, or how many standard deviations away from the average to judge closeness against the p-value. The more intuitive way to think about this is it's kind of the probability that I'm outside the confidence interval, right? Just like we talked about 1 minus alpha being the confidence inside the confidence interval, 1 minus alpha is the probability that I'm outside, or how likely that I'm not in there. And remember, when I'm outside the confidence interval, that means the p-value is small. And if the p-value is small, I want to reject. So I don't reject the hypothesis if I'm inside the confidence interval. I do accept it. I reject it if it's outside of it. It's the same thing as the p-value being small or large. The level of significance, usually when you do a hypothesis test, you designate the level of significance, and being 0.01, 0.05, or 0.1 are common values. And the reason for that is this corresponds to confidence levels of 99, 95, and 90. And so for the same reason that we choose confidence levels between 90 and 99, we choose significances like of 0.01, 0.05, and 0.10, because it's a compromise between accuracy and error. So we don't want to be in error too often. An error in this case would mean that if I choose a level of significance that's too high, right, that would mean our confidence is very low, and so we would fail to accurately capture the population characteristic more frequently. So our hypothesis test result would be wrong. So we tend to want to have high confidence, at least 10%, that our hypothesis test is correct. Now, what level of significance or how much confidence you want is usually selected by the researcher or given by the problem. But in terms of hypothesis testing, it defines how unlikely the value, the sample statistic that we get, if the null hypothesis is true. So in other words, it really tells us how often we're going to be wrong about our result. Fortunately for you, the practice of actually doing hypothesis testing is pretty straightforward. You don't have to know all the details. Just remember the p-value approach is that the probability of obtaining a test statistic more extreme than the actual example given the null hypothesis is true. And so what we think about is that if the p-value is small, how small? Smaller than the level of significance, then we reject H0. H0 is probably not true. If the p-value is large, how large? Larger than the level of significance alpha, then we can't reject H0. It's very important to know that we state things as we can reject or we cannot reject. We never state that the null value is true. We don't ever get evidence that the null value is true. We can only get evidence that the null value can be rejected in favor of the alternative, because the alternative is the only possibility if H naught isn't true. But we don't ever test for the case that H naught is true. It's always H naught is false or we don't know. So that's an important distinction. And it has to do with the value, the p-value being less than alpha. So alpha is the level of confidence, let's say 5%. 1 minus alpha, so alpha would be the required level of significance. 1 minus alpha would be the required confidence to conclude the alternative. In other words, that if we are, let's just say that alpha is 5%. 1 minus alpha would be 95%. So the required confidence is 95%. We have to be at least 95% confident to conclude that the alternative is true. In other words, to reject H naught. How much is that confidence? Well, the p-value tells you exactly how much confidence we have. So the p-value is the probability of getting that test statistic, right? In other words, outside that confidence interval. So if 1 minus the p-value would be called the actual confidence in the alternative hypothesis. So if the p-value is, say, let's say they get a p-value of 1% or 0.01, then 1 minus the p-value would be 99% or 0.99. That would be our actual confidence. Now that means that would be 99% confident that the alternative hypothesis is true. That if alpha, if we're testing at a significance level of say 5%, then we need 95% confidence at least to conclude A or the alternative, but we actually have 99. So 99% is higher than 95%. So we are more confident than we need to be to conclude HA, and so we conclude the alternative is true, rejecting H naught. Again, in practice, this is a lot easier to do than it is to talk about. So here's the 4 steps of a hypothesis test for you. First, state the hypothesis, write it down as H naught and HA, statistically speaking. Figure out what the p-value is using Megastat, using the appropriate hypothesis test. Then make your decision by saying, is that p-value smaller than the level of significance? If it is, reject H naught in favor of the alternative. If the p-value is larger than the required level of significance, then you cannot reject. Another way to say that is that 1 minus the p-value is the actual confidence that we have in the alternative. And if that's greater than the 1 minus the level of significance or the required confidence, then you can conclude H naught. Otherwise, don't. Now, let's take a look at this in practice for an actual thing. If we're going to have a hypothesis about the population mean, and we're going to assume that's what's unknown, just like in our estimate problem, we're also going to assume that the standard deviation is unknown. And for this, we will use the t-test. Just like for the confidence interval estimate, we use the t confidence interval estimate. We're going to use the t-test to do our hypothesis testing. Now the t-test has a couple of assumptions, or has an assumption associated with it. Just like with the confidence interval estimate, we assume that the population is normally distributed. The reason why we have to assume the population is normally distributed is that for the p-value to be accurate, we have to know how to calculate the probability that I'm in or not in that confidence interval. So to calculate that confidence interval accurately, I have to know that the population is normally distributed so that I can calculate that confidence interval, and then I can calculate the probability that I'm not in it or in it. Okay. The nice thing is that if the data is not known to be normally distributed, then we can, if we take a large enough sample, and in our case we're going to say the rule of thumb is that we have at least 30 sample points, then we don't have to worry about the population being normally distributed. This is a very important assumption to pay attention to, that if our sample size is less than 30, then we need to check that the population is normally distributed, or at least normal enough, so that we can get an accurate p-value. If we don't get an accurate p-value, then our test results will be inaccurate or unreliable. Okay, because we won't be able to calculate those p-values. If the sample size is at least 30, we don't have to worry about this being normally distributed. We just go ahead and do the test. If the sample size is less than 30 and it's not normally distributed, then we can't really use the t-test, and we can switch to a different population test, such as the Wilcox test for the population median. Let's take an example here. Let's look at batteries, and let's just say that we're testing a bunch of batteries, and we want to know, if I'm manufacturing batteries, is the capacity, the average capacity of batteries, less than 140 ampere hours? So we might take a random sample, and again, it's important to take a random sample. That way we get a representative confidence, or an accurate confidence interval, and that way we can calculate a good p-value. So it needs to be a random sample. A random sample of 20 batteries. Notice that it's less than 30, so we'd have to check that our population data is normally distributed. Let's just say we get a sample mean of 138.47 ampere hours. Now, it seems kind of close to 140, but is it close enough to conclude that the capacity is less than 140? I don't know. Let's find out. Let's just say it has a standard deviation of 2.66. That's the sample standard deviation. And we want to test at the 0.05 level significance. Otherwise, 95% confidence level. We'd like to know whether it's true, whether the average capacity is less than 140. So we write down our hypothesis. Population mean ampere hours greater than 140, or the alternative is less. Why is it less than 140? Because the question said the average capacity of batteries is less than 140. Because this doesn't have equality, this is going to be the alternative hypothesis. So there it is. And so if that's the alternative, then the exact opposite is going to be my null hypothesis, greater than equal 140. Now, in Megastat, to do the t-test, it's gonna have to calculate the degrees of freedom. So for the t-test, the degrees of freedom is just one less than the number of sample points. So I have 20 sample points. One less than that is 19. If I run this through Megastat, you'll see that I get a p-value of 0.009. So what does this mean? Well, first of all, I notice that 0.009 is less than 0.05. In other words, this p-value is lower than the required level of significance. Because this p is low, the null, 0, the H null, has got to go. So it means this is going to be rejected in favor of this, because this value is less than that value. So the p is low, lower than this. The null's got to go. That means that there is evidence to support that, based on the 20 sample points we took, that the mean value, the mean ampere hour capacity for our batteries is less than 140. Okay, how confident can we be at this? Well, we know that we're at least 95% confident. Why? Because 1 minus alpha is the required level of confidence. So that would be, if we want it, we're testing at the 5% level, the level of confidence is 95%. So we're at least 95% confident. But the p-value will tell us just how confident we are. Looking at 1 minus 0.009, that gives us the actual confidence. In other words, 99.1. So 1 minus 0.009 is 99.1%. That's the actual confidence that the mean ampere hours is less than 140. Again, 1 minus the p-value is the actual confidence. And you notice that 99.1 is greater than 1 minus 0.5, right? Or 95%. So 99.1% means I'm more confident than the required confidence of 95%. Okay, so let's take a look. Now that was a one-tailed t-test. One-tailed meaning because we're looking at something that is greater than or less than, not equal to. And so the confidence interval, we only care about whether it's in the confidence interval, either above it or below it. We don't, not both sides. So let's say we're at Walmart and we're looking at teddy bear sales, and we notice that the weekly sales in hundreds of dollars is over 10 stores was 800, 1100, nothing, 400, 700, 800, 10, 1,000. etc., etc. So let's test this at a 0.5 level of significance. Is there evidence that the average bear sales, weekly sales, is more than $500? Okay, so we just turn that into a statistical question. More than 500, population mean weekly sales greater than $500. Therefore, the exact opposite. Now, this has the inequality in it, so it's the alternative. So the opposite is less than or equal to 5. The significance level is 0.05. Degrees of freedom, there's 10 sample points, so there's only 9. And so we go to Megastat and we plug this in, and we get a p-value of 0.111. So 0.111 is not less than 0.05. So this p-value is not too low. So we cannot reject H naught. In other words, there is not sufficient evidence or insufficient evidence that the population mean weekly sales is greater than 5. So that's exactly the way we'd state it. Because the p-value of 0.111 is greater than the required level, 0.05, equivalently we could say because our confidence, our actual confidence, which is 1 minus 0.01 or 88.9 or 88.9%, is less than the required level of confidence of 95%, there's insufficient evidence that the population mean is greater than 5. Notice that we always talk about the alternative. We don't talk about the null. We always talk about we can only be 88.9%. So even though that's pretty confident, it's not confident enough. Okay, so in Megastat, this might be the way it looks. We would have our sales here. We would give it as data input by selecting the data input here. Our hypothesized mean is 5, corresponds to whatever's in the alternative. So we state whatever in the alternative. Okay, it's meaning that the 5 is greater than, right? The population mean, says population mean is greater than 5. So that's the same thing as this. And you don't need to state the alternative because it knows that the alternative or the null is the exact opposite of this. And again, we select either t-test or z-test. Now we select the t-test because the standard deviation is also not known. If we did know the standard deviation, we'd select the z-test. 95% confidence because we're testing at the 0.5 level of significance, which corresponds to 1 minus that 95% confidence. Hit OK, and it'll give us our test results like this. Hypothesized value of that, okay, greater than that. We get the mean sales of that, standard deviation is that. It calculates those from the data. Standard error is calculated, that's all calculated. I get the t-statistic, and then it says my value is 0.1109, or rounded up 0.111. And it's a one-tailed upper test. This is greater than 0.05. Therefore, I cannot reject the null, which is that the mean is less than or equal. That means I don't know. There's insufficient evidence, okay, that it's greater than 5. Okay, let's look at a two-tailed test. Let's say I work for the FTC, and a manufacturer detergent says that the weight, this Federal Trade Commission by the way, that the mean weight of this detergent as packaged is 3.25 pounds. Let's take a random sample of 64 containers. I calculate a sample average to be this and a standard deviation of that. Let's test it at the 99% confidence level, or the 0.01 significance, that the mean weight is equal to this. So the mean weight is equal to that, or is it not equal to that? Now notice that we have 64, a sample of 64. In these other ones, we did not have a sample of at least 30. So in these cases, we should check whether this data is normally distributed or not to meet the t-test assumption. In this case, we don't need to bother because there's more than 30 data points. So we state the hypothesis. Okay, mu is equal to 3.25. That's going to be the null because it has the equality. So the alternative is not equal. Alpha is equal to 0.5. Plug it into megastat, we get a p-value of 2.209. That means the actual confidence, which is 1 minus that, is 0.792. So we can be approximately 79.2% confident that the mean is not equal to 3.25. Well, the required level of confidence is 99. Well, 79.2 is much less than 99. Equivalently, 0.208 is greater than 0.01. Since it's not less than, we cannot reject this. And so there is not sufficient evidence to support that it's not this. Does that actually mean that our mean detergent weight is 3.25? No, it doesn't mean that. What it means is that based on our sample of 64, right, that we don't have evidence to say that this is not true. So in other words, it may not be true, but it could be true. If we did have, the only thing we can test for is there evidence to reject it? If we did find that this p-value is less than that, then we would say, yeah, there is evidence to support that it's not equal to that. But in this case, there's insufficient evidence to say that. All we can say is that, well, it may or may not be equal to 3.25. In other words, undetermined. Let's look at how can we extend this? We can take this idea of looking at one population parameter to comparing populations parameters. So let's take two independent populations. Two independent meaning that we're comparing two things that don't have a relationship to each other. We're just assume they're not related to each other. So let's just say that an economist wishes to determine whether there is a difference between mean family income for households in two socioeconomic groups. So if we look at, say we have a low, we might want to look at the mean family income for, two A and B. So we might want to compare the mean income between A and B and see if they're equal or not equal. Notice that there are two groups here. In this case, we actually have a numerical and a categorical variable. The numerical variable, of course, is going to be family income, and the categorical variable is going to be the socioeconomic groups. In this case, two of them. Here's another one: an admissions officer for a small liberal arts college wants to compare SAT scores from educated rural high school students and urban high school students. So we might have SAT scores. That's going to be our numerical variable. And our categorical variable is going to be rural versus urban high schools. Okay, so in this case, we'd say it's a numerical variable that's going to be split up by a categorical variable, each with two categories. So how would we look at this? Well, one way to look at that is by comparing them by subtracting the means and assuming that we want to know what is the population mean for group 1 minus the population mean for group 2. And if they are the same, if the population mean for 1 is the same as 2, then this difference will be 0. If it's not equal to 0, that means they're different. So what we want to do is test the hypothesis that the difference is either 0 or not 0. Okay, so the assumptions for this test we're going to make is that that the standard deviation is about the same for both populations. They're independent samples. In other words, the samples they're not only random samples, but I didn't sample one with respect to the other. In other words, if I'm looking at the socioeconomic groups and incomes, I'm not going to select people from one socioeconomic group based on what I selected from the other. So there's no relationship. And that the populations are approximately normally distributed. If they're not normally distributed, or we don't have at least 30 in each, we can use other tests like the Wilcox and Mann-Whitney test. So let's take a tangible example. Let's say we're a financial analyst for Charles Schwab, and we want to look at the yields between two different stocks on the NASDAQ and the New York Stock Exchange. Let's just say that we collect the following data: that we collect 11 stocks from the NYSE and 15 from the NASDAQ, and that we get a yield of a sample average of 3.27 from New York with a standard deviation of 1.3 and a 2.53 yield from the Nasdaq with 1.16. Let's assume that both the yields for New York Stock Exchange and Nasdaq are normally distributed, and we see that the standard deviations are pretty close. The rule of thumb is that no one is more than twice the other. So these are pretty close. How would we see if these means are the same or different given these standard deviations? Let's test the hypothesis that they are the same or different at a 0.05 level. So we write the hypothesis up as the difference between the Nasdaq and the New York Stock Exchange is 0. In other words, they're equal or not equal to 0. Okay, at the alpha level of 0.05, we plug this into Megastat. We get a p-value of 0.1397. Well, because this is greater than 0.05, we cannot reject this. Now, there is not sufficient evidence. There is insufficient evidence to reject this, or there's insufficient evidence to conclude that the means are different. How confident are we? We're only 86.03% confident. We need to be at least 90% confident. So there's not much evidence that the population means are different. In other words, does that make them the same? No. It doesn't make them the same. We just don't have evidence that they're different. In this two-sample t-test and confidence interval for mean and megastat would look like this. Put our values in, and notice instead of giving the data, since we have the sample means and sample standard deviation, we just give it the summary inputs here. And the hypothesis would be the difference compared to independent groups. Hypothesis difference is 0, and we're saying the alternative is not equal, 95%. T-test pooled. Pooled meaning that they are variances are about the same. We would use this one if the variances were not the same. Variance meaning the standard deviation. And if we knew the standard deviations, we'd use the z-test. So here's the output result from Megastat that you might see. All we really care about is this p-value here. What would happen if the data was not normally distributed? So if the data is not normally distributed, maybe we would use the Mann-Whitney test. So the Mann-Whitney test would be the same hypothesis, but instead of the mean, we'd be looking at the population median. The population median is more robust, and it's a different statistic, but again, it sort of represents the average. And the Mann-Whitney test would say, so we'd write out the population medians are equal, population medians are not equal, run it through the Mann-Whitney test. Again, we only care about the p-value. P-value of 0.5346 is greater than our required level, which is 0.05. So we can only be 46.54% confidence that the population medians are different. Again, you can see an example of this in our Excel proportions. Okay, that's a lot of stuff so far, but let's move on a little bit more. You might want to take a little break and come back. So far, we've only been talking about numerical data. We've talked about numerical data for one sample now, and we've talked about numerical data for one population, one and two numerical data with two populations that were, or if it's one numerical, one categorical, we made more populations by splitting that numerical up by the categories, okay, which gave us more populations to consider. Now let's consider categorical variables. Well, if we have categorical variables, then what we're interested in is the population proportion. We want to know what is the proportion that's in one category, and the opposite would be the proportion in the other category. So what we want to do is we would use the z-test for a proportion. And the z-test for a proportion would be you set up the hypothesis, except for instead of mu, it would be for the population proportion pi. Okay, so if we say that the population proportion that we're speculating, our hypothesis, is pi, then the number of samples, or the number of things in that population in that category that we're interested in would be n. Okay, so n is the number of things in the category that we're interested in. Pi would be the population proportion that we're speculating for that category. Now there's a condition, just like instead of normally distributed, we have this condition that the number of things in the category that I'm interested times the hypothesized population, and the number of that times 1 minus that is greater than 5. So we have to have at least 5 for each of those. It's a pretty mild condition. Then we would use the z-test from Megastat. So here's an example. Do ranch-style homes make up less than 50% of the population of homes? Okay, so we might go look at our ranch-style homes in our real estate example spreadsheet, and we would say, are there more than 50% of them, based on the samples that we have, ranch-style? Okay, so the opposite would be they're not ranch-style. Maybe we have 108 homes, and we found that of that sample of 108 homes, that 54 of them were ranch style. So that 54 is n, right? And pi would be 0.5, because we want to know if fine. So we want to know the hypothesis again. Do ranch-style homes make up less than 50%? So less than population proportion of ranch-style homes, less than 0.5, 50%. The exact, again, this has the inequality, so it's going to be the alternative. Therefore, the opposite is going to be the null, which is greater than or equal to 50. If we run it through the z-test in Megastat, we get a p-value of 0.0271, and we see that 0.0271 is less than 0.05. Therefore, we do have sufficient evidence to reject this in favor of this. So the evidence is supporting that the alternative is true. How confident are we? 1 minus this p-value, which is 97.29%. So we can be 97.29% confident that the proportion of ranch-style homes is less than 50%. Okay? Interestingly enough, if we did a equals and not equals, we would have found that the null hypothesis would have been acceptable. In other words, we couldn't reject it. Why? Well, because we see that we have evidence to say that it is less than. So if there's evidence that it's less than, then there has to be evidence that it's not equal. Can we find evidence that it's not equal to? We don't know, because it could be also greater than. So that's an interesting little tidbit. You should try that out. What about two categorical variables? This is where people really get confused, but we could try to compare two categorical variables. So when we do two categorical variables, we use the chi-square test. Here's an example. Let's say we're looking at our real estate data, and we want to say, do 3 different school districts have the same percentage of ranch, tri-level, and 2-story homes? So how would we figure that out? Well, out of 108 homes, we reveal the following. Let's just say school district 1, 2, and 3. Okay, we see that this is our one categorical variable. I'm either in school district 1, 2, or 3. And the other variable is the other categorical variable, style ranch, tri-level, and 2-story. So we want to know, do they have the same percentages of the different school districts have the same percentages of ranch, tri-level, and 2-story homes? Maybe we're interested in finding a particular kind of style home and we want to know, are they available in all school districts, or are there some school districts that have more than others? So this two-way table summarizes how many ranch in school district area 1, how many ranch in school district 2, tri-levels in school district 1, etc. So this is a two-way table just back from our regular descriptive statistics. So the way that we look at this is we use the chi-square. We can set up the hypothesis that says that there is a relationship between school district and style of house. Equivalently, there's a relationship between a style of house and school district. So relationships go both ways. Relationship means that the fact that I'm in a certain school district will influence what style house, or if that doesn't make logical sense, the style of house that I have influences what school district I'm in. Again, you have to determine which logically makes most sense. So the hypothesis would be no relationship for the null, and the alternative would be relationship exists. That might seem a little weird for you because we talked about the alternative has the not equal sign. But if you look very carefully, you'll think about, well, what does it mean for something to have a relationship? Well, for two categorical variables to have a relationship, it kind of means that the probability, right, of, say, ranch style, say the probability of, say, school district given ranch style house is going to be equal to the probability of being a ranch style house and or multiplying by the probability of being a ranch style house. Equivalently, we can say that, hey, if these things don't have a relationship, then if I look at the frequency or the probability of things in school district run given the ranch style, that should be the same as the not of the probability of having of being in a certain school district without worrying about the ranch style or tri-level or two-story. In other words, the style house has no influence on that. So you think about that. If there is equality, in other words, the probability of this given this is equal to the probability of that, that means no relationship, right? No relationship means they are equal. If they are not equal, means the probability of one given the other is not equal to the one without it, then a relationship exists. We'll take a look at that further. But the basic idea is just remember that the alternative is relationship exists and no relationship is the null. So if we run it through our chi-square, this particular data, we put this table into our chi-square on Megastat, we'll get a p-value of 0.0005. That's less than 0.005. Therefore, we're 99.9% confident that there is a relationship between school district and style home. So the interesting thing that we might want to find out, so if there is a relationship, then something must be influencing that. Like, what is the thing? That means that there are school districts that have higher percentages of ranch, tri-level, or two-story. There are school districts that have lower ranch, tri-level, and two-story. Well, which ones are those? So we can find those by doing a more careful investigation. You can see in this case that a follow-up analysis suggests that SAD1 has fewer ranch homes and more tri-level homes than expected, and the reverse homes for 3. So we'll take a look at an example problem of how to figure that out. We look at what I call the Fee, Fi, Fo, Fum table for that. So that's your introduction to all this. It's now time to get some real examples of this and then work some problems. So see you in class, and talk to you